Have you ever tried to really get a grasp on like some big scientific idea or like some complicated tech thing, you know?
Yeah.
It can feel like you're just bombarded with all this information and it's hard to sort through it all.
Just drinking from a fire hose, isn't it?
Exactly. And that's really what we're trying to do with this deep dive. We're taking these really interesting research articles and trying to extract those key nuggets of insight.
So it's less overwhelming.
Exactly. So you can actually use these insights to understand these complex topics.
Right. Think of us as your, I don't know, your information Sherpas, maybe,
Yeah, guiding you through the complexities of all
to
this.
the summit of understanding.
Exactly. And today, the summit we're aiming for is all about something called relational reasoning and how it can seriously power up your scientific thinking.
Oh, this is a good one.
Yeah, we're looking at this article called Enriching Students' Scientific Thinking Through Relational Reasoning, Seeking Evidence in Texts, Tasks, and Talk. It's by P. Karen Murphy, Carria M. Firetoe, and Jeffrey A. Green, and it was published in Educational Psychology Review.
Back in March 2017.
That's right. So relational reasoning, what exactly does that mean?
Well, in a nutshell, it's about making connections. It's about seeing how different concepts, ideas, pieces of information, even skills relate to each other.
So it's not just knowing a bunch of facts, it's knowing how those facts fit together.
Exactly. And the article argues that this ability to connect the dots is absolutely essential for really grasping STEM, science, technology, engineering, and math.
Especially in light of the next generation science standards, the NGSS.
Right. The NGSS really emphasizes understanding the interconnectedness of things rather than just isolated bits of knowledge. And we're going to explore how relational reasoning shows up when you're reading, when you're working on problems, and even when you're discussing ideas with others.
It's a pretty big deal. So let's talk about how this all links to the NGSS. The article mentions that there's been this shift in science education, partly because of concerns about STEM preparedness.
Yeah, there's this worry that students aren't leaving school with the skills they need to really thrive in a world that's increasingly reliant on science and technology.
And this has led to a big push towards what they call a three-dimensional approach to science education. So what's the idea behind that?
Well, it moves away from this old school approach of just memorizing facts and formulas.
Okay.
The NGSS really focuses on three dimensions.
Hmm.
So first, you have these scientific and engineering practices. This is all about actually doing science, experimenting, and solving problems.
So it's hands-on.
Exactly.
Hmm.
And then you have these cross-cutting concepts. These are big overarching ideas that connect different areas of STEM, like, for example, cause and effect, or systems and system models.
Oh, I see. So these are like the threads that run through all the different scientific disciplines.
Yes, it's about seeing the bigger picture, how things relate across different fields.
And then the third dimension is the core ideas.
Right, these are the key concepts within each specific subject,
Yeah.
the fundamental principles. But the important thing is, it's not just about learning these ideas in isolation. It's about understanding how they connect to the practices and the cross-cutting concepts.
So it's all about building a web of understanding.
Exactly, seeing the relationships between different parts of STEM. And that's where relational reasoning comes in. The article argues that it's essential for several of these key NGSS practices.
Okay, let's break those down. So the first NGSS practice they discuss is developing and using models. How does relational reasoning play a role in how we use models?
Well, first of all, it's important to understand that models aren't just these visual aids, right?
Yeah.
They're tools for understanding. They help us go beyond what we can directly observe and kind of imagine a world that we haven't seen yet.
Right.
Like, how do we picture something like geologic time?
Yeah, or like the inner workings of an atom.
Exactly. Things that are either too vast or too tiny for us to directly experience.
So we need models to help us conceptualize them.
Right. And this is where it gets really interesting because research by Resnick and colleagues in 2016 suggests that our ability to imagine these unobservable worlds is directly linked to relational reasoning.
Oh, interesting. So how does that work?
Well, they looked at why people have such a hard time grasping things like, really huge scales like geologic time or
Yeah.
really tiny scales like nanoscience.
Yeah, it's hard to wrap your head around.
Right. And what they found is that we often rely on analogies to try and understand these things, like comparing the immense timeline of Earth history to a 24-hour clock, for example.
Right, that's a common one.
But here's the catch. If the analogy isn't carefully chosen, If it doesn't clearly show which parts are similar and which parts are different, it can actually lead to flawed mental models.
Oh, I see. So it's not just about finding any analogy, it's about finding one that accurately maps the relationships between the source and the target.
Exactly, like that 24-hour clock analogy.
Hmm.
It might not really capture how gradual many geological processes are.
It oversimplifies it.
Yeah. So Resnick and his team suggest that it's more effective to start with basic concepts that lend themselves well to making good comparisons. And they emphasize how important it is for educators to really probe students' understanding of these analogies.
So asking questions like, what aspects of this analogy are helpful, or what aspects might be misleading?
Exactly, to ensure that the model is actually supporting their understanding through relational reasoning.
It's making me think about all the times I've tried to understand something using an analogy, and maybe I wasn't using the best analogy.
It happens to all of us. Analogies are powerful, but they can also be tricky if we're not careful.
Okay, so that's developing and using models. The next NGSS practice the article talks about is analyzing and interpreting data. And it seems like this is another area where being able to see relationships is really crucial, especially when you're trying to understand how text and graphics relate to each other.
Right. Danielson and Sinatra did some really interesting research on this in 2016. They point out that graphics can relate to text in several different ways. It's not always just a straightforward illustration.
Oh, interesting.
So, for example, a graphic might highlight some anomaly in the data, like a sudden spike in cholera deaths in a specific location. Or it might present a contrasting viewpoint to what's being said in the text, like imagine a diagram comparing different models of how the Earth orbits the sun.
So the graphic is adding another layer of information, not just repeating what's in the text.
Exactly. It might be showing an exception, a contradiction, or a different perspective. But what Danielson and Sinatra found is that students often default to looking for just analogous relationships between text and graphics.
So they assume the graphic is just going to illustrate the text in a straightforward way.
Right, and that's not always the case, which is why they argue that when you're designing instructional graphics, you need to be very intentional about making it clear what kind of relational thinking is needed to understand them.
So you need to signal to the learner, hey, pay attention here. This graph is showing you an exception to the rule, or a different way of thinking about this concept.
Exactly. And I think this has implications for all of us, not just students. Sometimes we feel overwhelmed by charts and graphs, and it might not just be because they're badly designed.
Right. Maybe we're just not sure how to relate them to the text. We're looking for the wrong kind of relationship.
That's a really good point. So are you struggling with the graphic itself or with figuring out how it connects to the text? It really highlights the importance of understanding these different ways of seeing relationships.
It's like having different lenses to look through.
Exactly. Okay, so let's move on to the third NGSS practice they highlight, which is engaging in mathematical and computational thinking. Now, you might think this is all about numbers and formulas and algorithms.
Which can be a bit daunting for some people.
For sure. But the article suggests that there's actually a lot more to it than that, and that relational reasoning plays a key role here too.
I'm intrigued. Tell me more.
Well, thinking mathematically at a deeper level involves being able to compare different problem-solving methods and understand the relationships between those methods.
So it's not just about getting the right answer, it's about understanding how you got there and why one approach might be better than another in a particular situation.
That's exactly it. Richland and her colleagues, in a 2016 study, they argued that this can be really challenging for students, and it requires effective teaching. They suggest that explicitly teaching students about different types of relational reasoning can actually make it easier for them to compare different mathematical procedures and solutions.
So if you're good at spotting those relationships between different approaches, you're better equipped to analyze and evaluate them.
Exactly. And they found that this kind of explicit instruction about relational reasoning can actually decrease cognitive load.
Oh, that's interesting. So it's not just about making things more complex, it's about providing the right kind of scaffolding to help students see the connections and make sense of it all.
Exactly. And this benefit of having a broader view of relational reasoning beyond just looking for similarities is a consistent finding in the research.
So it's a really valuable skill to cultivate.
Definitely.
All right, and finally, the fourth NGSS practice they discuss is engaging in argument from evidence. This seems pretty straightforward.
Yeah, on the surface, it seems like it's just about backing up your claims with data.
But there's more to it, isn't there?
There is. And this is where relational reasoning comes back into play in a big way. Research by Candu and her colleagues in 2016 has shown that relational reasoning is absolutely crucial for being able to critically examine your own understanding and revise it based on new evidence.
So it's about being able to compare what you already know with new information and potentially change your mind if the evidence suggests you should.
Exactly. And they talk about this process of considering what's analogous, anomalous, antinomous, and antithetical when you're evaluating different models or explanations.
So breaking it down, analogous is about finding similarities. Anomalous is about finding things that don't fit the pattern. Antinomous is about identifying contrasting ideas. And antithetical is about finding things that are directly opposed.
You got it. And Kendall's work really highlights how this kind of multifaceted relational reasoning is essential for that process of knowledge revision, of updating your understanding based on new evidence. It's about seeing how different pieces of information fit together, or maybe where they clash.
And being able to use that to refine your understanding.
Exactly. So you're not just blindly accepting new information, you're actively integrating it into your existing knowledge base.
It's like being a detective piecing together the clues.
I like that analogy.
So it's clear that relational reasoning is this underlying skill that's woven throughout all these NGSS practices. It's really central to scientific thinking.
Absolutely. It's not just a separate skill you learn. It's integrated into the process of doing science itself.
Okay, so the article then goes on to discuss a specific teaching approach called quality talk science, or QTS. And they argue that this approach can help students actually develop these relational reasoning skills that are so important for the NGSS.
Right. QTS is all about leveraging the power of classroom discussions to promote deeper learning.
So how does QTS work?
Well, it's based on the idea that learning is a social process, and it draws on elements from other successful discussion-based teaching methods.
So it's not just about lecturing at students, it's about getting them to actively engage with the material through dialogue.
Exactly. The main goal is to foster critical analytic thinking and reasoning.
Okay, so how is that done? What are the key components of QTS?
Well, they break it down into several parts. First, there's the instructional frame. This includes things like organizing students into small, heterogeneous groups and starting the discussion with a warm-up activity, often using what they call a catalyst worksheet.
So setting the stage for a productive discussion.
Exactly. And then you have the discourse elements, which are the types of questions and responses that are encouraged during the discussion.
Like, are they asking open-ended questions or are they asking for specific facts?
Right. And are students giving detailed explanations, or are they giving one-word answers? The focus is on high-level thinking questions and elaborated responses.
So really pushing students to think deeply about the material and articulate their ideas.
Yes. And then there are the pedagogical principles, which guide the overall approach, like the idea of gradually releasing responsibility to the students.
So over time, the students take on more of a leadership role in the discussions.
Exactly. And then finally, there are specific teacher moves that are designed to promote thinking and reasoning.
So things like asking probing questions or summarizing key points.
Precisely. And a typical QTS session involves the teacher leading these discussions using what they call authentic questions. These are questions that require students to think critically, make connections, and consider different perspectives.
So it's not just about reciting facts, it's about applying those facts to solve problems and understand complex phenomena.
Right. And they integrate the core science content into these discussions, so students are learning the material while they're developing these higher-order thinking skills.
It's a very intentional approach to teaching. And the article mentions that they've done research on QTS in high school physics and chemistry classes.
Yeah, and they've seen some really positive outcomes. Students who participate in QTS show improvements in their oral and written argumentation, and they're better able to reason about scientific phenomena, models, and data.
So the research is backing up the theory.
It is, and this is where it gets really exciting, because the article then goes on to give us examples from real QTS discussions to show how these different forms of relational reasoning actually show up in student talk. They specifically looked for analogy, anomaly, antinomy, and antithesis in the students' conversations.
So they were analyzing the types of connections students were making as they were discussing the material.
Exactly. Let's start with the hot packs example they give. It's a really good illustration of how these different types of relational reasoning can emerge in a classroom discussion.
Okay, walk me through it.
So the teacher starts by asking this question that gets students thinking about the difference between the molecules in a liquid versus the molecules in a solid.
Setting up an antithetical relationship right from the start.
Exactly. Asking them to compare and contrast these opposite states of matter. And student 3 jumps right in, describing how the molecules are more spread out in a liquid and more tightly packed in a solid. And then they even extend it to gases, talking about how the molecules are even farther apart in a gas.
So that's a clear antithetical response, highlighting the key differences between those states of matter.
Exactly. Then student 1 brings in the idea of crystallization, talking about how water or sodium acetate can crystallize into this lattice structure.
And they connect that sense of order to the concept of entropy.
Right, so that's analogical reasoning, drawing a parallel between crystallization and this idea of a lattice structure.
And then student one goes on to point out something interesting, something that doesn't quite fit. They say that usually forming bonds requires energy, but hot packs actually release energy when they solidify.
Right. So they've identified an anomaly, something that seems to contradict the usual pattern,
Yeah.
and that sparks further discussion and exploration.
It shows how students are actively engaging with the material, looking for inconsistencies and trying to make sense of them.
Exactly. They're not just passively absorbing information, they're actively constructing their understanding. And the article notes that in their data, analogy was the most frequent type of relational reasoning they observed. And we see another example of that in their discussion about why nail polish doesn't mix with water.
Right, I remember that one.
So student 6 asks this question about why the nail polish stays separate from the water. And student 5 gives a detailed explanation about molecular attraction and hydrogen bonding.
So getting into the scientific principles behind it.
Exactly. And then student 6 uses this really clever analogy. They compare the attraction between molecules to a couple who doesn't want to get a divorce.
Which is such a relatable way to think about it.
It is. It makes this abstract concept of intermolecular forces much more understandable. And interestingly, the second most frequent type of relational reasoning they found was antinomous reasoning.
Which is about identifying what something is and what it is not.
Exactly. And their example about color and light versus color and paint is a perfect illustration of this.
Right, student 6 asks how all the colors can combine to make white light, and they reference mixing paint as a comparison.
And student 1 immediately jumps in and says, this is not paint. Paint's different.
So very clearly distinguishing between the two.
Exactly. Student 1 is reasoning that light and paint create color in fundamentally different ways. And the article points out that this happened during a moment of exploratory talk where students were debating and trying to work through their ideas together.
So that disagreement actually spurred this deeper level of reasoning.
It seems like it. That back and forth exchange of ideas seems to be really productive for pushing students to think more critically about the relationships between concepts.
And the article notes that anomalous and antithetical reasoning were the least frequent types they observed in their data. They suggest that this might be because of the students' prior knowledge or maybe the specific tasks they were doing. Like, if the lessons focused more on models than on analyzing raw data, there might not be as many opportunities to spot anomalies.
That makes sense. The context definitely plays a role. But they did find that certain types of questions asked during the QTS discussions were more likely to elicit relational reasoning. Specifically, questions that asked students to make connections and questions that tapped into personal experiences.
So if you ask students to relate the material to their own lives or to other things they know, it encourages them to make those comparisons and connections.
Exactly. And they also found that those episodes of exploratory talk where there was some level of disagreement were strongly linked to relational reasoning. It seems like the act of working through a disagreement forces students to really examine the relationships between ideas more carefully.
It's like they have to justify their thinking and consider alternative perspectives.
Exactly. And finally, they found that over the course of the QTS intervention, there was a gradual increase in how often students use relational reasoning in their discussions.
So it seems like it's a skill that can be developed over time.
That's encouraging, isn't it? It suggests that QTS isn't just about getting students to talk more, it's about helping them develop a more sophisticated way of thinking about science.
Okay, so the authors then go on to connect their findings to the other articles in this special issue. They show how their research on QTS supports the ideas presented in those other papers.
Right. They make several interesting connections. First, they link QTS to the idea from Richland and colleagues that talk is a tool for promoting relational reasoning.
So just like discussing different problem-solving strategies in math can help students see the relationships between those strategies, discussing different scientific models can help them see the connections and differences between those models.
Exactly. And they give an example of a student who's looking at 4 different models of how airbags inflate, and uses antinomous reasoning to point out where those models disagree.
So the discussion is providing a space for that kind of comparative thinking to happen.
Exactly. And then they connect QPS to the work of Danielson and Sinatra on text-graphic relational reasoning.
Right. How do we make sense of information presented in both text and visual formats?
Exactly. And they highlight that the materials students read for QTS discussions often include both text and graphics that partially overlap, which is similar to what you encounter in authentic scientific materials.
So they're getting practice with that real-world skill of integrating information from multiple sources.
And they give an example of a student who refers to a picture of a hot pack to argue against a claim about how energy is released, using antinomous reasoning to define what energy is not.
So using the visual information to support their argument?
Right. They're showing how QTS encourages students to use evidence from both text and graphics and use relational reasoning to evaluate claims.
Okay. And then they talk about how QTS relates to Resnick and colleagues' work on understanding big concepts and scales through relational reasoning, especially through analogy.
Right. They use an example from a QTS discussion about uranium-235 fission. The text they were using compared the energy released to a tank of gasoline. And the student brings up this analogy during the discussion, talking about how it helped them put the immense amount of energy into perspective.
So the analogy, even though it's presented in the text, is further explored and elaborated on through the discussion, helping students really grasp the concept.
Exactly. And finally, they connect QTS to Kendi and colleagues' research on how we revise our understanding and correct misconceptions through relational reasoning.
So how do we use new information to update what we already know?
Right. And the example they give is a discussion about rainbows and nail polish, where one student uses an analogy to prisms to help another student realize that their previous understanding of how rainbows form was incorrect.
So they're using relational reasoning to identify a misconception and then correct it?
Exactly. It's a perfect example of how confronting conflicting information and using relational reasoning can lead to a restructuring of knowledge.
Pretty powerful stuff.
It is. And they wrap up by saying that their findings really suggest that QTS supports the development of relational reasoning abilities in a way that aligns with the NGSS.
Which is really the goal, right? To help students become more effective scientific thinkers.
Exactly. And they briefly mentioned this framework by Dumas for measuring relational reasoning, suggesting that QTS research fits into what he calls the in vivo category, which is studying reasoning in real-world settings.
So not just in lab experiments, but in actual classrooms.
Right. And they even propose that we could expand this category to include research on teaching interventions like QTS that are specifically designed to enhance relational reasoning.
So taking it a step further, not just observing reasoning in action, but actively trying to cultivate it through teaching.
Exactly. And they end by emphasizing the need for more research to really test the effectiveness of these interventions. Like, how can we design learning environments that explicitly promote relational reasoning in STEM?
It's a great question, and it leaves us with a lot to think about. So for you, our listener, as you reflect on all these different types of relational reasoning we've discussed today, analogy, anomaly, antinomy, and antithesis, which of these do you find most challenging in your own learning? When you're trying to make sense of something new, which of these trips you up the most? And why do you think that is? Maybe thinking about how you can actively look for different kinds of relationships between ideas could be a really powerful tool for deepening your understanding across all sorts of topics.
Something to ponder, for sure. Thanks for joining us for this deep dive into relational reasoning.
It's been a fascinating conversation, and if you're interested in learning more, we highly encourage you to check out the research articles we've discussed today.
You won't be disappointed.
Thanks for listening. We'll see you next time for another deep dive.